Going into day 5, high efficiency combinatorics and network scan matrix generation. So just quickly, combinatorics is a branch of mathematics that focuses on counting, arranging, and selecting objects. It plays a crucial role in coding by helping to solve problems related to permutations and combinations, which are fundamental concepts in computer science. Permutations are the arrangement of objects where the order matters, while combinations are selections of objects where the order doesn't matter. The mission briefing for today is that your objective is to build a memory-efficient, industrial-grade network discovery rule generator using combinatoric optimization. So imagine you're auditing a massive corporate infrastructure migration. The network engineering team has handed you a target list containing dozens of classless IP subnets, a massive array of critical compliance ports, such as SSH, RDP, WinRM, database ports, etc., and multiple transport protocols, TCP, UDP, ICMP. To configure the automated vulnerability scanners and validate firewall states, you must generate every single possible connection permutation, amounting to millions of distinct network evaluation vectors. If you attempt to compute, store, and iterate through this massive matrix using standard nested for loops and naive Python lists, your system will rapidly encounter an out-of-memory or OOM kernel panic or grind to a halt due to massive RAM overhead. Your mission is to weaponize the Python Itertools library to construct a high-speed, zero-memory footprint pipeline that generates filters and streams these matrices on the fly, ensuring your automated network discovery tools can run seamlessly on constrained engineering hardware. So the concepts we're going to learn today is memory-efficient stream processing, utilizing lazy evaluation to handle combinatorial data pipelines without allocating gigabits of RAM. And then we're going to look at combinatoric matrix design, Itertools.product, for example, generating Cartesian products of IP subnets, port lists, and protocols to simulate comprehensive network matrices. We'll look at permutations versus combinations in security, knowing when to leverage ordered structures versus unordered groupings for multi-hop pivot analysis and firewall rule verification. We're also going to look at performance evaluation of iterators, analyzing the memory footprint and execution speed advantages of iterator engines over standard list allocations. So going into the memory exhaustion tax list versus iterators. The most common anti-pattern in network automation is building massive data matrices using nested lists. So the naive list approach is when you list a comprehension or append items to a standard Python list. Every single permutation is calculated immediately and allocated a dedicated block of system RAM. Across a massive enterprise infrastructure dump, this creates an aggressive memory footprint that can trigger an out-of-memory crash. The iterator solution. An iterator uses lazy evaluation. It does not calculate or store the combinations ahead of time. Instead, it computes the next item only when explicitly requested. For example, in a for loop or via next, the memory footprint remains completely flat at constant time complexity, whereas if you are generating 10 combinations or 10 billion. So let's look at the absolute easiest example possible to see the difference between the list and iterators using a tiny pool of numbers. So imagine you want to pair 2 items from a list A with 2 items from list B. There are 4 total combinations. The naive list approach is the ego evaluation. Think of the list approach like buying a box of prepackaged donuts. So what your computer does is it instantly creates a box big enough to hold 4 slots, and it generates all 4 pairs and drops them into the slots. The iteration solution is the lazy evaluation. Think of the iterator approach like a donut machine at a dynamic buffet. It doesn't store anything ahead of time. It only makes a donut when you press the button. So if you import Itertools, my_iterator equals Itertools.product. So what your computer does is the memory is virtually empty. The machine is just sitting there waiting. You ask for the first item, next my iterator, the machine drops down 1, x. You process that item. You ask for the next item. The machine discards the old one, spins the gears, and drops down 1y. Because the computer only ever holds one pair at a time, the exact amount of space it takes up in memory is always exactly the same, whether it's processing 4 combinations or 4 billion. Moving on to Cartesian products and Itertools.product. In security automation, generating a Cartesian product means pairing every element of one set with every element of another. This is the exact mechanism used to generate a comprehensive network scan matrix. Instead of writing messy, deeply nested for loops that damage readability and slow down execution, Itertools.product handles this natively in optimized C code. For IP and IPs, for port and ports, for proto and protocols, target equals to IP port proto, import Itertools, and then you have the scan matrix Itertools.product with IPs, ports, and protocols inside. So pretty much, and the analogy is, why would you pair the elements? We have a firewall analogy for this. In network security, a firewall is a strict guard dog that evaluates traffic based on a set of rules. For a connection to be allowed or blocked, the firewall has to check multiple distinct properties at the same time. Who is talking, the source target IP address, what door are they trying to enter, the port number like 22 for SSH or 443 for HTTPS, and what language are they speaking, the transport protocol like TCP, UDP, etc. A security vulnerability scanner or a firewall rule audit cannot just check these properties in isolation. If you only check if an IP is valid, you don't know what services it's exposing. If you only check if port 22 is open, you don't know which machine is exposing it. To build a reliable defense matrix or run a comprehensive security audit, you must cross-reference every single possibility. This complete cross-referencing is what we call a Cartesian product. So for example, let's look at a practical scenario. Suppose your script needs to audit a micro subnet with just 2 IP addresses, checking for 3 critical compliance ports across 2 protocols. So we have set A, the IPs, set B is the ports, and set C is the protocols. If you don't pair them completely, you leave a massive blind spots in your security visibility. By generating the Cartesian product, you ensure every single permutation is accounted for. So here's the exact matrix generated with when you pair every element of one set with every element of the other. So from this example here to here, the Cartesian product of two sets A and B is defined as the set of all ordered pairs AB, where A is an element of set A and B is an element of set B. It is denoted as A times B and represents all possible combinations of elements from the 2 sets. That's just for further clarification. Moving on to permutations versus combinations in security architecture. So choosing the correct combinatoric tools depends entirely on whether the order of your sequence matters. So remember, for permutation, the order matters. The pairing node A to node B is considered completely distinct from node B to node A. So the security use case is multi-hop pivoting and lateral movement pathing. If you are simulating how an attacker might pivot through compromised infrastructure assets, traveling from the web server to the database server is totally different network path than traveling from the database servers to the web server. Whereas in combinations, the rule order does not matter. The pairing node A, node B is identical to node B, node A. So the security use case here could be mutual authentication or network isolation audits. If you are verifying whether 2 subnets are properly segmented from each other, you only need to test the connection between them once. So testing subnet A, subnet B covers both directions of isolation. Just for further clarification, I've written down a couple of examples for permutations and combinations. So think of permutations like booking a flight ticket. If you buy a ticket that goes from Melbourne to Los Angeles, that is completely different than booking a trip from Los Angeles to Melbourne. You are using the exact same 2 locations, but changing the order completely changes the direction, the itinerary, and the experience. The security parallel pivoting, an attacker compromising a web server and using it to pivot into a protected database server is a critical security breach. However, a database server initiating a connection out to a public web server is an entirely different traffic flow that triggers different firewall rules. The direction dictates the threat landscape. Whereas think of combinations as the handshake. What does it matter? Think of combinations like a handshake between 2 people, Alice and Bob. If Alice shakes hands with Bob, Bob is simultaneously shaking hands with Alice. It happens at the exact same time. It doesn't make sense to say first Alice shook Bob's hand and then Bob shook Alice's hand. Right? The pairing exists as a single mutual event. Security parallel, so we have network isolation. If you're auditing whether the HR subnet and the finance subnet are properly isolated from each other, you only need to test the link once. So if HR cannot talk to finance, then finance automatically cannot talk to HR. Testing the pair covers both directions of your isolation check and is not entirely necessary. So quick summary, permutations are a 2-way street with 2 distinct lanes. A to B is different from B to A, whereas combinations are a bridge connecting 2 islands. Once the bridge exists, A to B is exactly the same as B to A. The final theory pillar that we're going to talk about is combinations with replacement. So Itertools.combinations_with replacement. So the rule is that order does not matter, but elements compare themselves. So the security use case is for loopback or same host inter-process communications. This is used when testing rules where a service on a host talks to another service residing on the exact same host. For example, verifying container-to-container communication, sharing the same loopback interface. The analogy here is leaving a note on your own fridge. So imagine a household where people leave notes for one another on the refrigerator. The standard combination, Alice leaves a note for Bob. That is a pairing of 2 different elements. Alice Bob, combination with replacement. Alice writes a reminder note to herself and sticks it on the fridge. She is the sender and she is also the receiver. The pairing is Alice and Alice. It is still a valid communication link within the house, but it doesn't involve an outside party. The replacement part of the mathematical rule simply means that once you pick Alice as the sender, you don't throw her name out of the hat. She goes right back in, allowing herself to be picked as the receiver too. The security parallel, loopback and IPC. In networking and container security, this is exactly how a computer talks to itself. Normally a container like a web app front end talks across the network to a completely different container like a database. That is a standard pairing of container A and container B. However, modern microservices are often bundled together inside the same host or Kubernetes pod, sharing the exact same local network space called the loopback interface or 127.0.0.1. When the web app front end wants to send a log message to a local logging agent living on the exact same host, it sends the data out and it loops right back into the same machine. This system is pairing with itself, host A to host A. Why we need this in a scan matrix? When generating automated tests to audit firewall security profiles, you can't just test if server A can talk to server B. We also have to generate rules to verify that local services are safely permitted to talk to themselves internally without getting blocked by poorly written global network policy. you want to see loopback in action, I did a case study video titled CCNP case study. So you can definitely look into that and see how it pairs in an actual topology as well. So the summary reference table, we have the product function, permutations, combinations, and combination replacement. Orders matters, yes, yes, no, no. Allows duplicates, yes, from different sets. No, no, and yes. The primary security application is generating full IP port protocol scan matrices, modeling attack graphs, lateral movement, and proxy chains. Then we have subnet isolation checks and firewall zoning audits. And then we have loopback testing and same host service communication audits, as you can see now. Now moving on to the pseudocode. So we have the function, which is the stream underscore scans targets. You have the subnet, ports, protocols, and exclusions. We want to generate every combination of subnet, port, and protocol dynamically. For each subnet port protocol in Itertools.product, subnet ports protocols, loop through individual hosts inside the subnet one at a time. So for each IP in subnet.host, check if the specific target is on the block list. If IP port is in exclusions, continue. If the target, yield the target immediately without saving it to a list. Otherwise, so how it executes in production. So you set target matrix equals stream underscore scans targets. The loop pulls one item out of the generator at a time. Memory usage never goes up because only one target exists in RAM at any moment, as we touched about before. And for each target in target matrix, run underscore firewall underscore test target. So here's the final full code. Just give you a moment to read through it before I deep dive into the line by line meaning. Okay, so the first line that we're going to look at after importing Itertools and importing IP address is the exclusion underscore set equals to setting exclusions. What does this mean? Well, what it does is it converts the raw exclusions input into a Python set. Why we do this is because checking if an item exists inside a standard list gets slower and slower as the list grows, linear time. A set uses a hash table layout under the hood, making lookups nearly instant, no matter how many millions of rules are on your block list. So just further explanation, in the line, the set command takes a standard list of items and converts it into a set. A set is a unique connection of elements using the hashing that we touched on before to organize data rather than ordering items sequentially like a list. While this matters for performance, if you leave exclusions as a standard list and you ask Python if target in exclusions, Python has to start at index 0, check it, move to index 1, check it, scan all the way to the end of the list. Whereas if you have 10,000 exclusions, it might take 10,000 checks for every single IP address you evaluate, known as linear time complexity. The set approach is instant. When you convert it to a set, Python runs each exclusion through a mathematical hashing function to calculate an exact location in memory. When you check if target in exclusion set, Python hashes the target and jumps directly to that memory address instantly. It takes one single check, whether you have 5 exclusions or 5 million. This is known as constant time complexity. I did a deeper dive on time complexity in day 4, so check that out for a more in-depth evaluation. Next time we're going to look at is for subnet string port protocol in Itertools.product subnet ports protocols. Well, what does this mean? Again, we're also lazily generating a combination of subnet, port, and protocols, and I hope you understand why from what I explained earlier. But what this does is it leverages Itertools.product to pair every single subnet string with every single port and every single protocol. Why it matters, it acts as an optimized single pass iterator running at C-level speed. If you pass in 2 subnets, 5 ports, and 2 protocols, this loop will prepare to execute exactly 20 times, matching them up smoothly without nested Python loop overhead. Next line is network equals to IP address dot IP underscore network subnet underscore string strict equals false. So what it does is it takes the raw string like 192.168.10/24 and converts it into a rich Python network object. The strict underscore false flag ensures that if someone accidentally passes a host IP like this 192.168.1.5 instead of the true network ID, Python automatically masks it down to the base network without crashing. Then we're going to move on to for IP and network hosts. IP underscore str equals to str IP. So what it does is it loops through the usable host IP addresses inside the specific network block and casts the IP object into a clean string. Why it matters, so crucially, host is a generator. It does not build a giant list of 254 IPs in memory. It calculates the next IP string only when the loop steps forward. Just another deep dive into the string function. It takes an object and converts it into a clean string text representation. In the code engine, the variable IP inside the network host loop isn't exactly text yet. It is a specialized complex data object created by IP address module. So we have the before and the after. So why we do it here? For compatibility. The raw IP object cannot easily be combined with strings inside formatted print statements or passed by text-heavy security modules. Recasting it as a text makes it compatible with standard Python operations. Matching exclusions. Our exclusion set stores items as text pairing, like 192.168.1.1, 22 to see if the current host matches. We must convert the active IP object to text so it properly aligns with our rule checklist. Only a couple more things to go. But we have the if, so skip the target if it's in the exclusion set. We have if IP underscores str, port in exclusion set, continue. So before letting a target vector pass down the line, it checks if the specific IP port combination matches a highly protected asset, like a core router interface or a critical server. If it matches, the continue statement acts as a gatekeeper, skipping the rest of the block and moving straight to the next IP address. Then we have the yield. What it does is, instead of using return, which stops the function completely, or append, which saves it to a list, we use yield. So we use yield because it pauses the function right here and passes the single completed target tuple, the three values tuple, down to whatever loop called it outside the function. Once that external step processes the target, the execution snaps right back here to grab the next IP. So it's a very useful command for this sort of situation. So the execution environment, what we're going to do in this part is that we define the input parameters. Obviously, this will be the actual logs coming in, but we do this for the simplification purposes and to explain the concepts. So what it does is it sets up the raw inputs for your network audit. It specifies two separate subnets, each containing 254 usable host IPs, 3 critical ports to scan, and a single transport protocol. The exclusion is that it also defines a specific hazard safeguard. If the engine generates 192.168.1.1 on port 22, typically the network's main gateway router, it should be skipped to avoid accidentally flooding a production interface with scan traffic. And the final 2 points is the target matrix equals the stream underscore scan underscore targets. So this instantiates the lazy generator pipeline. So what it does is this calls the function we built and assigns it to the variable target underscore matrix. Crucial detail, this line does not actually run the loops or generate the targets yet. Because the function uses yield keyword, calling it simply creates a generator object. It sits in system memory completely idle, occupying almost 0 bytes of RAM, waiting for a command to start spitting out data. Final thing that we have here is for target in target matrix, print, testing target, IP, target, port, and protocol. What this does, this for loop is the engine's for set handle. By iterating over target underscore matrix, it requires the very first element from the generator, how it handles memory. The generator wakes up, builds the first target tuple, for example, 192.168.1.2, 22, TCP, passes it into the loop and it instantly pauses. The print statement executes reading the properties via index positions. The loop goes to the next iteration, the old tuple is cleared from memory, and the generator wakes up to calculate the next target in line. So that's it for day 5. Just to recap, we configured the automated vulnerability scanner and validated firewall states. And we weaponized the Python Itertools library to construct a high-speed, zero-memory footprint pipeline that generates, filters, and streams these 3 matrices on the fly, ensuring that the automated network discovery tools can run seamlessly on constrained engineering hardware. Thank you very much, and I hope to see you in the next day's challenge.